The next speaker, I would like to welcome Claude Florin from Fast-Tree 3D, and he's talking about flash LiDAR-based on-time resolved single-photon imaging sensors. So Claude, the next 8 minutes, the floor is yours.
Yeah, thank you, good afternoon. We were asked to be visionary at this conference, so we had the vision of a very fast three-dimensional imaging that would also give you two-dimensional picture, and that would also process on the same chip some of the analysis of the image we take. So that is our goal. And the reason we do it is already this morning at the show, we saw many use cases where the detection of fast motion is still a bit of a problem, primarily in transportation, in logistics, but there are always some corner cases where the speed, the low latency, the emergency reaction has a value. One well-known case is that about 250,000 pedestrians and bicycles are hit by cars every year, and that's not because the camera are bad, but acquiring these multiple frames and processing is often too slow when the pedestrians was occluded. So that's one of the many use cases where speed and low latency is an advantage. And to solve that, we decided to provide a camera that would also be extremely cheap using commodity component like vertical cavity emitting laser, or the same CMOS imaging technology that is used for image sensor. And the benefit of doing that is shown a bit of that slide. We're able to do a flash LiDAR. There's something that basically nearly has just a chip and a lasers, and the detection is made with single photo detector that operates typically 1,000 times faster than a camera imager. And the illumination is performed by VCSEL, illuminating 10 million times per second a scene. So with all that data, we can be fast and accurate. And of course, traditional laser scanning, which is designed to optimize often power and range, could not cover these kind of fast detection. So our plan and what we're showing at the booth here is we're showing a prototype chip, exactly that chip, and we're showing a demonstrator of the system, so it shows that we can detect and that we can cover these use cases. Our intent is next year to produce a single chip with 40,000 pixels, which is really a great breakthrough. So the detector we show, you can see it's this green part with single photo detectors that measure over 60 meters at 2 centimeter resolution, and it has a blue part that essentially is embedded in the current demonstrator and performs some calculation and allows you to test in application. We've tested it to detect under the highest sunlight this year, pedestrian and cyclist very fast at 35 meters detection, and we know it could be further. We also detected that we can process all that information. So for example, the information we provide is of course the 3D time of flight, the distance, but also the quality control on every pixels at the frame rate. And lastly, the 2D image, which will help you merge with an imager. And we can filter based on that. I can take out the background, which is the noise in the image. I can see in the 3 targets, all that at the frame rate, processed by a processing unit in which you can write your own custom software. Let me show you 3 examples why control of a chip is important on the chip. On one hand, if we control the pulse of that little laser here, in the new eye safety standard, we can multiply with 1 nanosecond pulses by 100 the emitted power in eye safe mode. That will give you wider field of view or range. If we can control also the frequency and the shift to encode these pulses, then we can operate multiple cameras without any form of interference or bad reflection. That is often one of the challenges when you want to do surround application, and we control it very nicely. The last type of control is obviously in time of flight. The problem has often been the sunlight, coming from the sun and being higher than your laser. I am showing here three types of performance coming from data processing. One is statistical control. You perform histogram of your measurement. That's a very classical way of doing direct time of flight. The second one, you will compare among multiple pixels if they're receiving the front edge of a pulse or if it's the sun that is random. So that's called coincidence. And the third time, you can operate the whole camera in global shutter mode, but you could operate every single pixel like a camera that opens fast and measures the different part of the images without being blurred by the sun. So these are the reasons you want to do it. Now, next year we'll announce everything in a single chip that is comparable to Apple and Sony announcement. It's in the Apple iPhone. These are people we know very well, so everything in a single chip. Don't want to say more, but we'll kind of discuss the details, because I'm very proud at the booth to have at least one of my co-founder, Lucio Carrara, who invented some of that technology years ago, and some other members of the team. And 10 years ago, he did a chip, had a career at Photonics developing image sensor. My other co-founder did the Microsoft Kinect and produced demonstration with 1 million pixel at 100 frames per second last year, and the first worldwide 3D stack chip 4 years ago. So we're definite that the prototype and the chip we're showing will have a very good delivery in the future. So to sum up, we have a demonstration. It solved real-life problems that were not solved up to now, and we have an efficient delivery. So we'll be glad to discuss with you if you've got questions now or later, or in our booth, or at other opportunities. Thank you for your attention.
Thank you, Claude. Any questions? Jury members. Oh, and by the way, all you listening here, feel free to ask questions through the chat. So I can see it here and I can read it out. But here, Mr. Erzu has a question, please.
So thank you very much for your presentation. Can you give me an idea about the prices for the future at volumes of 10,000 sensors per year?
So if you would produce 10,000 detector, there will be about 40,000. I'm going to talk about the bill of material. We primarily would like to sell chips, okay? So you would be at chips that would have a bill of material about 30, 40 euro, that kind of thing, and would go down to maybe 1/4. So that gives you an idea of the chip. We certainly want the camera to be all lower than 100 euros.
Okay, thank you.
Thank you. Any other questions from the jury members?
I hope this is not unfair, but there's other companies that do low-cost solid-state LiDARs like Terabi. And could you just say where you really have the edge or do something completely new compared to others that are out there?
So I don't think today there are other companies than Sony and Apple that would deliver you 40,000 pixels at 60-meter range in that domain. So that's the first thing. And although you did mention another company that I respect a lot, they would be our customer. Terabi uses ST microelectronics proximity sensors or the Photonics chip. So we would be a provider of these chips to Terabi, would be then an integrator.
That was helpful, clarifies it, thank you.
Yeah.
Thank you, Claude.